think, let's erase the second problem. So I think, let's see, if you're talking about, I don't know. If you're talking about now that the line is perpendicular to this, oh, where are you? Is perpendicular to this? Oh, that's a problem.
So they wouldn't do that?
That's a problem, because let's look at a line here. And we're told that this line goes through a certain point. Let's see, well, it might work. Yeah, I guess that, yeah, because of that it would. Let's see. How would I get perpendicular to that? I don't know how I would do that. So that's a clue right there. Because we would need, to get perpendicular, we would need another vector, so we could do a cross product. And all I know about this point line is that it's got this point, and it's perpendicular to this, oh yeah, I wouldn't know. There could be all kinds of things that are perpendicular. Oh, hello. Yeah, there could be all kinds of, this is actually not a good, Jenna, that is not a good problem, all right? There's all kinds of lines that could be perpendicular. It could go out in this direction, infinite number, I can't get a unique line. So you're asking a bad problem, okay? So, yes, so the bottom line is I'm not going to be asking a bad problem, all right?
Can you only have 34 too? I forgot to completely write down the problem.
Oh. All right. 34 in what section?
You gave us a hint, I just couldn't figure it out.
Okay, all right. Maybe we'll just, okay, so this is number 34. It goes through the points 1, 1, 2, 3. We want an equation of a plane, and it contains the line x equals 3t, y equals 1 plus t, z equals 2 minus t. Okay, it contains the line. Okay, why don't I just take a leap and we'll just try to do that as the first thing. All right. And hope that I don't mess it up. Yeah, turn in my homework here. Let me just, why don't you guys, just it'd be faster if you guys just came up and grabbed one of each of these. All right. One of that, and one of that. All right. And then just put your homework over there. Homework number 2. Okay. First of all, homework number 2 then, that's due today. And the first thing I'm going to do in class actually is a student here had a question on one of the problems on homework number 2, so I'm going to do my best effort to hope I don't mess it up and do that. That's the first thing. And then test 1 is a week from today. And of course, the week before a test is always a week of work, whether we like it or not. That's how it works here. So there's a homework that's due on Friday, next Friday, homework number 3, and then there is a take-home quiz that is also due at that time. And then in addition, I have provided you, all of this stuff, of course, is also on Blackboard, a practice set, and I will be posting the full solutions to the practice set on Blackboard on Sunday, all right? So the practice set also has some concepts on it that you need to be able to know, all right? If you can do pretty much that practice set, you're good to go, all right? But of course, doing the homework and the take-home quiz are also going to give you the practice that you need, all right? And also they're graded, so that's also an incentive. So what was asked here is this problem here. It's problem number 34 from section 12.5. And we're asked to find the equation of a plane. And we're told that the plane contains this point, the point 1, 2, 3. And we're told that the plane also contains this line that's written in parametric form. All right. Now, let's remember what we need for an equation of a plane. For the equation of a plane, we need a point on the plane. Well, that's already given to us, so that's a nice thing, all right? But we also need an orthogonal vector to the plane, or a perpendicular vector. So those are the two things we need for the equation of a plane. All right, so let's see here. We know that this plane contains this line, which is described by this set of parametric equations. So this set of parametric equations gives us a direction vector of this line. What would be the direction vector of this line? Yeah. 3, 1. 3, because that multiplies the t there for the x. 1, that multiplies the t for the y. And minus 1, that multiplies the t for the z. All right. So this vector basically can be considered as on the plane. All right? Now, to get at the orthogonal vector to the plane, we need two distinct vectors that are on the plane, right? And we'll do their cross product. Make sense? So let's get another vector on the plane, and then we can do a cross product. And that'll give us our orthogonal vector. You okay with me so far, Cassandra? All right. So how can we get another vector on this plane? Well, look at this. We've got a point on the plane. You get a point from the parametric equation. Yeah. We've got this parametric equation that gives us a line on the plane. So basically, let's plug in a value for t here. That'll give us a point on that line, right? Take the difference to the other point that we're given And that'll give us a displacement vector that's also on the plane. So what's the easiest value of t to work with here? Let's work with 0. So this point, let's see, 0, 1, and 2 is on that line, which is on the plane. All right. Now this other point that we're told is on the plane is 1, 2, and 3. So the difference of the 2 points will give us a displacement vector. So a displacement vector on the plane, is going to be, let's just do the difference of the coordinates. The one vector minus the other. So this will be 0 minus, 0 minus 1, negative 1, 1 minus 2, negative 1, 2 minus 3, negative 1. Okay, I'm doing it the hard way. All right. I could have done it the other way too and had all positive values. So what we can now do is you know what? I'm going to do that right now. Why don't I just is there any reason why I can't just multiply all of this by minus 1 and also have a vector that's going to be on the plane? Can't I just also say 1, 1, 1? Because if I had done the other way, if I had started, this is my end point, this is my beginning point, I would have gotten 1, 1, 1. All right? So let's use that one, since we can reduce our minus signs. So we need to do a cross product, I, j, k, and the two vectors is 1, 1, 1. And what's our other vector? 3, 1, and minus 1. Okay. So let's see. For the I, we get rid of the first row and first column. What are we going to get there? Minus 1, minus 1. I think we're going to get a minus 2, right? Times the I. You all right with that? And then remember, for the j, we have to put a minus there initially. And again, let's cross out. And I get minus 1, minus 3. So I have a minus 4. But since I have to put a minus in front of it, that becomes a plus 4. And then for the k, let's cross that stuff out. I get a 1 minus 3, which is a minus 2. So my orthogonal vector, I hope this was correct, is 2, 4, and negative 2. Let's see if that works out here with these. That's minus 6 and 4. Yeah, that'll work out. And with that'll work out. So it is, and I'm checking to see that this is orthogonal by doing a quick dot product with the other two vectors. If I get a 0 with the dot product, then vectors are orthogonal, right? Okay, so this is our orthogonal vector. So this is orthogonal to the plane, and the point on the plane is 1, 2, and 3. So, what can I get immediately if I know the coordinates of the orthogonal vector to the plane when I write the equation of the plane? These give me my coefficients for x, y, and z. Minus 2x plus 4y minus 2z. Right there for my equation of the plane. This is my orthogonal vector to the plane. I can get my coefficients of x, y, and z right off the bat. Now this is equal to some, then we put equal to some number d. Well, I can figure out what my number d is by plugging in a single point on the plane, and I'll figure out my number d. So let's plug in 1, 2, and 3, I guess, and solve for d. So we have minus 2 times 1 plus 4 times 2 minus 2 times 3 equals d. What do we get? 8 minus 6, I think we get 0, don't we? Or am I wrong? 8 minus 2 is 6, 6 minus, yeah, we get 0. So therefore my answer, my final answer then, is minus 2x plus 4y minus 2z equals 0. Or, what can I do to everything in that equation? I can divide by 2, or minus x plus 2y minus z equals to 0. And that's the equation of my plane. Okay? All right, you're welcome. All right, where are we here with this? Okay. All right, so we're on, so last time we talked about vector functions, and we talked about getting the derivatives of vector functions. This time in section 13.3, we're talking about finding arc length and curvature, something that's called curvature, of a space curve. All right. Okay? So, let's see. We have a space curve, and it's given by a vector function r of t equal to f of t, g of t, h of t. This is a vector equation of the space curve. All right. We can also then get a parametric equation of the space curve. Let's see. I didn't have. Let me just check something here for a second. Make sure that. Basically, the space curve can be represented by a vector function. Let me just put that here. Space curve can be represented by a vector function. By a vector function. So we have, with our vector functions, we have the three components, f of t, g of t, and h of t. And so so if we break down the r of t into the x, y, and z components, we then have parametric equations. Of the space curve. That's going to be x is equal to f of t, y is equal to the middle function g of t, z is equal to the last function h of t, all right? And we're going to be assuming that these three functions are continuous and have derivatives. So we're just going to assume continuous functions, there's no breaks in the curve, and they have derivatives. So shall we say nice functions? All right. So, fact, now we're getting into the arc length. The length of the curve, the length of the space curve from, say, the parameter t equaling a to the parameter t equaling b is this. We'll call it capital L, and it's equal to the antiderivative from a to b of the square root of the square root of the sum of the squares of the derivative. The square root of f prime of t squared plus g prime of t squared plus h prime of t squared dt. All right. let me put an asterisk here. So it's really an extension of, I guess, the Pythagorean theorem here. This is really an extension of the arc length when we had just a regular function of one variable, okay? This is just an extension of the other arc length, where y is equal to f of x, all right? So you need to make sure that you remember this formula here. Another way, of course, of writing this is the integral from a to b of the square root of, I can write this as dx dt and then square it, plus dy dt and square it, plus dz dt and square it dt. That's both equivalent expressions. All right. There is actually, I guess I'll get into this, yeah. There really is kind of a shorthand way to write this. Okay, let's look at basically the function r prime of t. Well, we know that r prime, if we take the derivative of our vector function, that's going to be the derivative of each one of the components. And then if we look at the magnitude of this vector, this is a vector, its components are the derivatives. If we look at the magnitude of this, this is the square root of the squares of the components. F prime squared, g prime of t squared, plus h prime of t squared. So this whole expression can actually be written a little bit more quickly by just writing it as the magnitude of the tangent vector, which is the derivative vector. All right, so therefore we could say L is equal to the integral from a to b, and I'm going to replace this big thing with just this, the magnitude of r prime dt. Okay. Now let's just get to a concrete problem and so we can hopefully feel a little bit more comfortable with this. So this would be a kind of problem that you would see either on homework or on a take-home quiz or anything, or on the test maybe. Find the arc length of this vector, this base curve, given by r of t given by 12t, 8t to the 3/2, and 3 times t squared, where for t going from 0 to 1. All right. Now what we need, so this is our f of t, this is our g of t, and that's our h of t. All right? So we have to get their derivative, right? So f prime of t is equal to what, 12? G prime of t is equal to what? 12 times t to the 1/2 power, right? 12t to the 1/2 power, and h prime of t is equal to what, 6 times t? So therefore, let's do it, so we have our integral, and it's from 0 to 1, that's our values for t, and we have to square all of those individual derivatives. So 12 squared is going to give me 144. When I square g prime, I'm also going to get 144, but I'm squaring t to the 1/2 power, so that just gives me plain t. And then when I square h prime, I get 6 6s is 36 times t squared. So I get that. And let's see here if we can try to simplify this, because it will simplify. Trust me. What number can I take out from under the radical to help simplify this? Uh, 12. Yeah, I can actually take out 36. It's a nice perfect square. 36 divides into 144 4 times, right? This is 4 times 36, 4 times 36. So every term has a 36 in it. So if I take out the 36, then that's the square root of 36. So I'm going to put it out front as a 6, okay? And then I put what times what's left, and let's see. So let me lead off with the t squared. So I'm just going to have a plain t squared plus 4 times t plus 4 dt. All right? And so this problem is set up to be nice because what do we have underneath that radical? T plus 2 squared. Isn't that nice? So we have a perfect square trinomial under the radical. This is t plus 2 parentheses squared. We're doing the square root of that, so we just end up with t plus 2. Notice here we're only talking about t going from 0 to 1, so we're going to have a nice positive number underneath there. So this is going to give me the integral from 0 to 1 of 6 times just plain old t plus 2. Okay. All right. So let's get this antiderivative. This is going to be antiderivative of 6t plus 12. So that's going to be what? 3t squared plus 12t when I work that out. And I'm taking that from 0 to 1. And, okay, that's it then, really. I plug in the 1, I get 3 plus 12. I subtract the zeros, I just get 0. So I find out here that the length of this line is a nice 15 as my answer, okay? So you'll have type of thing that'll work out where you don't get a horrible potential antiderivative to have to figure out, okay? Question on just figuring out that arc length. What you do have to remember is the formula. Now, I will give you a heads up for anxieties about the test. The first part of the test actually is going to have some matching stuff. I've got some stuff over here, and I've got some matching stuff over here. So if you're able to figure out the matching, that this equals this, that equals that, then you're going to have those formulas right in front of you, all right, so that if you need them later on in the test, you can go back to the first page, all right? But you have to be able to at least match them up, all right? If you can't match them up, you're in trouble, all right? But matching them up is an easier kind of thing to do, I think, than just having to have them cold, all right? All right. Basically, let's then look at curvature here. Well, I want to mention this one thing. It's an FYI, and then we'll talk about curvature. There's what's called an arc length function, and we're not going to get too much into this, but let's just say hint, you might want to be able to at least recognize it. Arc length function, again, we have a curve, the space curve given by r of t equal to f of t, g of t, h of t, all right? I know it's hard to read that, I'm sorry. And we're saying for t, from A to B. Bigger than or equal to A, less than or equal to B. All right. Then the arc length function is, we can call it f of t is equal to this. It's the integral from our initial point to some value of t times, integral of the square root of these squares. Square root of f prime squared plus g prime squared plus h prime squared dt. All right. So this is actually a function because this upper limit here is a variable. So this is a function of t, which is why it's called an arc length function. So we just have a variable up there. And so let's just put it this way, know how to recognize this. Okay. All right. Now, we have actually computing the arc length, we've done that, and just being able to recognize the arc length function. Now I just want to talk then about the second item here in this section, and that's called curvature. Well, all right. Before we get into this, let's give you a definition. A vector function r of t is called, quote unquote, smooth if its derivative is continuous, if r prime of t is continuous, and if r prime of t never equals the zero vector. This is the zero vector. All right. All right. And remember, r prime, this is the tangent vector, r prime of t. Basically, to put this in English is this, that a smooth curve doesn't have any sharp corners. It does not have any sharp corners. All right. So the deal is the derivative of the tangent vector is continuous, which means it's smooth, it doesn't skip, and it never equal to the zero vector. All right. Now, so by sharp corners, we're talking about, say, if we have a space curve x, y, and z, and so it was moving along very nicely, and then all of a sudden, whoop, right here, it kind of goes like that, and then down, and then keeps doing its thing. That would be a sharp corner right there, okay? So we don't have that if the curve is smooth. Now, recall that the unit tangent vector is given by, we call it capital T of t, and it's defined as, well, it's the tangent vector, r prime of t, divided by the magnitude of the tangent vector. So this is a unit vector. It has length 1, And this up here in the numerator, this is our tangent vector. But because we divide it by its magnitude, it becomes a unit vector. All right? We have length 1. Now, this tangent vector, this unit tangent vector, changes direction more quickly when the curve bends or twists more sharply. So this unit tangent vector changes directions more quickly when the curve bends or twists more sharply. And let me show you then what I'm talking about with this. Okay, let's look here at, where is it? Here. Right. Okay. Now, what we have here is, we have this particular space curve. Actually, this is just a two-dimensional curve. We only have an x component and a y component. So the x is an ln function, the y is a sine function. This purple vector here that's just touching the curve, that is the unit tangent. It's unit tangent vector. So let's just notice here the curve doesn't really change much. So when we start moving this, oh boy, that's very sensitive. When we start moving this along, the tangent vector doesn't change direction too much. But then when we head down here, once right here at the bottom, this notice right here, that tangent vector starts to flip because that curve is changing direction. Now it's going to kind of just stay in the same direction as the curve is kind of flat, but then up here at the very top, it's going to flip again very quickly because the curve is changing direction. And then it's going to again kind of stay in the same direction. And right now it's going to flip very quickly here. Note, look at that. It just goes very quickly because look at how sharply that curve changes down there. Then it's going to go up again, not change much, and then it's going to flip very quickly again, and we just continue this process. Now let's look, I think we have another curve, couple of curves here. Let's look at curve number 4. Oh yes, curve number 4 is a good one. Curve number 4 here, now we have a three-dimensional curve. This looks like one of those strange ones that I drew the other day on the computer. So this one is, we have three components, x equals t, y is a cosine of a sine times a sine, z is a sine of a cosine times a cosine. All right. The blue line right here, this is going to be the unit tangent vector. So it doesn't change much, but then this curve starts changing direction. It's going to flip. Then it's going to flip again, keep changing, 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 changing. Now, in these areas here, notice, in these areas where the curve changes, that's where you would consider the fact that it has more of a curvature, right? Because it's curving. In those areas where it has more curvature, notice that is where the tangent vector there is flipping direction a lot. So right here, we've got a lot of curvature right here. That purple vector is changing direction quite a bit. Then here we've got curvature again, it's changing direction. And then right here we've got this very tight loop, a lot of curvature here, and this tangent vector is flipping around 360 degrees, and then it goes out. So this unit tangent vector, the more it changes, the more curvature our curve has. Okay. All right. So let's put that down, and okay. So first of all, let's just give a informal kind of intuitive definition. Curvature is a measure of how quickly the curve changes direction. A straight line, a straight space curve that's a straight line, it's going to have a curvature of 0 because it never changes direction. It always keeps going straight, right? Now here's the first of two mathematical equations for curvature, definitions of curvature, that they are equivalent to each other. So, the curvature of a curve, and we call it a kappa t. So it looks like a K, it's a kappa. Is kappa t is equal to the magnitude of the derivative of the unit tangent vector divided by the magnitude of the tangent vector. So in English, this is what it is. It's the length of the derivative of the unit tangent divided by the length of the tangent vector. Okay, again, this thing right here, this is the tangent vector. All right. Now, again, you need to be able to at least recognize that formula. There is an equivalent formula that I also want to give you that you also need to be able to recognize. I'm not going to prove that this is equivalent. The textbook does prove that it's equivalent. Another equivalent definition of curvature is this. Definition of curvature is kappa of t equals, all right, again we have a numerator and denominator. The numerator is the magnitude of the tangent vector cross product with r double prime of t divided by the magnitude of the tangent vector taken to the third power. All right, so let's look at this. This is the, remember, r of t, that's our curve. So we have, and it's actually a vector function. So we find r prime of t, we find r double prime of t, we have to do their cross product, we get their magnitude, and then we divide it by the magnitude of r prime to the cubed. All right, so that sounds perhaps a little horrific, and it can be a little tricky. I'm not going to say that it can't be, but let's try to work this out here with one example. And so here, let's do this one first. This example is given in the textbook, and it says this: show that a circle of radius equal to some number a has curvature equal to 1 divided by a. Now here we're only talking about a two-dimensional. This is a two-dimensional. So let's try to figure this out now. We're going to be using we're going to be using the top formula for this. The top formula in this case is a little bit faster than the bottom formula. All right. First of all, we need to figure out what is our vector function here. It's only on the x and y plane. So, we're talking about a circle. So here, I guess I should draw this. X, Y, and Z. Here we're talking about basically right here a circle around the origin, and so we've got an X component and a Y component. The Z component is going to be 0. So basically we can look at it as A times the cosine of t for the X component. Because remember, we normally do cosine for the x. We can do a times the sine of t for the y component. And then the z component is 0. It's just flat on the xy plane. So this is our vector function. And now we need to get what? We need to get r prime of t. So let's get the derivative here. Okay, derivative of a times the cosine is what? Negative a sine of t. Derivative of a times the sine is a times the cosine of t. And the derivative of 0 is 0. Okay. Now, we want to use this formula here, t, capital T prime of t. Remember, t is equal to what? It's equal to the vector function divided by the magnitude of the vector function. So what do we have here then? Okay, our vector function, what we have is minus a sine of t, a cosine of t, and 0. But what is going to be the magnitude of that vector function? It's going to be the square root of the squares of the individual components. It's actually going to be a squared sine squared of t plus a squared cosine squared of t plus 0. And so that simplifies in the denominator to just a. So sine squared plus cosine squared is 1. So this is what we get then for t, our unit tangent function is just going to be in the denominator a, and then we have minus a sine t, a cosine of t, and 0. And of course, when I divide by a with each of those terms up there, I get minus sine of t, cosine of t, and 0. So that's our unit tangent function. Now to use this definition then, I need to take the derivative of the unit tangent function. So now let's get t prime of t And so derivative of the minus sine is the minus cosine. Derivative of the cosine is the minus sine, and we have a 0 there. So this is our capital T prime. Now, in our formula for K of T, our curvature, the top part is the magnitude of the derivative of T. And then the bottom part is the magnitude of R prime of T. Well, what's the magnitude of this function of this vector right here? We take the square root of the squares of the components. Right, we're going to get a 1. Minus cosine T squared minus sine T squared plus 0. This is all going to be 1 in the numerator. Now, in the denominator, what did we get here? Whoops. We had already figured out that the magnitude of R prime of T was equal to A. Yeah. So that's A, and so we have an A there. So therefore, our curvature is indeed equal to 1 over A. So this tells us, so you say, big deal. This tells us that a little circle with a little radius that means A is small. If the denominator is small, the curvature then is going to be big, right? Because if we divide by a smaller number, we get a bigger number. So it's going to have a bigger curvature. If I have a circle that goes for a whole mile around, has a huge radius compared to a little tiny circle like this, we're going to have a very small curvature. So we have a bigger circle with a bigger A, a bigger radius. This is going to, 1 over the bigger number is going to give us a smaller curvature. Just like they thought the Earth was flat. So big radius, it just seems like there's no curvature to it. It's just flat. That's just because it's a really big, well, we can look at it as a circle, all right? Okay. All right. I think we better take a break before we do this next problem, all right? So let's take it's 5 to 11, so let's take a break. That makes the shadow worse. I'm going to have to ask somebody why there's this shadow up here, because that's bugging the heck out of me, and so that's all that counts, that it's bugging the heck out of me. Oh, wait a minute, what happened here? What did I do here? That also is messed up. Okay, there we are. So I'll see if I can look into that. What I can do about that shadow, so in case you guys are thinking about it. Got any ideas, Nelson? Yeah, I don't know. Okay. So this example is this. Okay, we're wanting to find the curvature of that twisted cubic that I had shown you the graph of the other day. So it's a vector function where we have t squared, and t cubed as our three components. First, we want to find the curvature in general, and then we're going to find it at a specific value of t where t is equal to 0. And I'm going to use this formula here, the alternate formula for curvature, and I'm thinking that generally this one will be a little bit more user-friendly. Okay, so that's just an FYI for you guys. So what do we have? So we have this formula in front of us. So obviously what we first have to get is the derivative r prime. So let's go on and do that. And so that's going to be 1, 2t, and 3t squared. And then notice what else we have to get. We have to get then r double prime. So let's go on and do that. Derivative of 1 is 0, 2, and 6t. So we have that. All right, what else do we need to get here to plug into this formula? We need to get the magnitude of r prime, so why don't we figure that out? The magnitude, okay, so that's going to be what? The square root of the squares of the components, so that's going to be 1 squared is 1, 2t all squared is going to be 4t squared, and then 3t squared, we square that, that's going to give us 9t to the 4th power, and that's all under the square root radical. Okay, now what else do we have to get here to be able to use this? We've got to get the cross product of r prime and r double prime. Okay, so let's do our I, J, and K here, and let's put in r prime, 1, 2t, and 3t squared, and then put in r double prime, 0, 2, and 6t. All right, so let's bite the bullet and figure this one out. It's not too bad, I don't think. For the I component, what are we going to have? We're going to have 2t times 6t, so that's 12t squared. And then we're going to take away 2 times 3t squared. We're going to take away 6t squared. So our component for the I is going to be 6t squared when we do that. All right. Now let's do the j, and remember we have to put a minus in front of that. So let's look at the component, what we get when we take off the first row and second column. That one's a little easier. We just have 1 times 6t minus 0. So therefore, we're going to have a minus 6t for the j component. And then the k isn't too bad either. We are going to have 2 minus 0, or just 2. So let me write this. I like to put this then in the, using the angle brackets. So the first component is 6t squared, second component minus 6t, the third component is 2. So that's our cross product. And then what do we have to do with this cross product? We have to get the magnitude of the cross product. So let's find the magnitude of 6t squared minus 6t and 2. So that's going to be the square root of the sum of the squares. So what's that going to be? 36t to the fourth, another 36 then t squared, and then a 2 times 2 is 4. All right. Okay. Okay. Before we go on here with this one, is there something I can just do a little bit with that last magnitude that I got? I can factor out, I've got a perfect square 4 that divides into all three parts of it. So I'm going to factor that out as a 2, and then I'm going to be left with 9t to the fourth plus 9t squared plus 1. All right, now it's just a matter of, okay, just do it in bite-sized pieces, and then you just put it together, okay? So the curvature in general, okay, it's going to be the magnitude of that cross product. So we just figured that out, and that's going to be 2 times the square root of 9t to the fourth plus 9t squared plus 1. Divided by, now what do we have in the denominator? It was the magnitude of the tangent vector r prime, but taken to the third power. So let's see here. Here we had gotten the magnitude of r prime right there. That's the square root of 1 plus 4t squared plus 9t to the fourth. I'm raising that to the third power. So let me write it in two different ways. So I've got the square root, this is of 1 plus 4t squared plus 9t to the fourth, and that's being raised to the third power. What's another way that I can write that denominator without the radicals? 3/2 power. I could also have written the denominator as 1 plus 4t squared plus 9t to the fourth, close parentheses, but raised to the 3/2 power. And I'd have the same numerator, 2 times 9, the square root of 9t to the fourth plus 9t squared plus 1. Notice that this that's still under the square root radical there. Unfortunately, I don't have any perfect square that I could use. That isn't a perfect square trinomial. So I'm just stuck with it. This is what I have. All right. So this is my answer in general, just using that formula. So my recommendation, just do the bite-sized pieces of it and then put it together. Now the second part then asks, well, what's the curvature when t is equal to 0, the parameter t is equal to 0? Well, that's just a matter of plugging in 0 for t. So here I have 2 times the square root, but when I have t equals 0, that's 0, that's 0, so all I have is the square root of 1. And then down below here, I've got 0 and 0. I just have 1 to the 3/2 power. So all I have, my curvature when t is equal to 0 is just the number 2. And so as with this twisted cubic, as t changes, obviously our curvature can get either bigger or smaller as we go along. Okay. So you'll have a basic curvature kind of problem similar to your homework or your take-home quiz. Now, all right. There is a last component here to this section. We talked about arc length. We talked about curvature. The last part of this section is if you go on and do any differential geometry, you'll actually be using this last part. So let's just say this. There are two, and I'm just going to put this in quotes, special vectors, and I'm going to show some pictures here. Special vectors that are perpendicular to the unit tangent vector, t. All right. They have names. They're called 1, the unit normal vector, and that is denoted with the letter N, capital N for normal vector. It's a unit vector also. And the second one is called the binormal vector, and with that letter B, it is denoted by capital B of T. Okay. Now let me show you a picture here of this. All right, we'll look at these a couple of times here. So this is actually this helix curve. X is the cosine, Y is the sine, and and Z is equal to T over 4. So this curve moves up like a helix, like a circular staircase, as T gets larger in value. Now, what we have here, notice here here's where we're located on the curve, and notice that there are 3 vectors that are sprouting out from that point. The vector in purple is the vector that we have seen so far. It's the unit tangent vector, where it brushes the curve as it goes along. The yellow or orangish vector is the unit normal vector. In fact, it labels them right over here. The blue vector that pops up is the binormal vector. All 3 of these are unit vectors. They all have length 1. And they're all perpendicular to each other. We have the tangent vector and the normal vector. They are perpendicular to each other, and those are both perpendicular to the blue vector. So kind of let me start moving this thing along. Oops. So as we move this thing along, of course, our purple tangent vector is going to change directions, and as it changes directions, our orange normal vector changes directions, and the blue binormal vector all change directions. But for every single point, they maintain the fact that they are all perpendicular to each other. What you can view these as is, look at this. In general here, we have the x-axis, the y-axis, and the z-axis, right? And they're all perpendicular to each other, those axes. What this gives us is for every point along the curve, it kind of gives us a little individual set of perpendicular axes. So in other words, no matter where we are, because these space curves can be really crazy, no matter where we are, we can actually very locally, when we're just talking about a localized area, we actually have our own set of perpendicular axes, all right? And that's where it comes into play in differential geometry. And I know it's used in relativity theory. When you don't have any frame of reference, there's no frame of reference, except we try to get a localized frame of reference. So these gives us kind of a frame, and it's called, the name of this, as you see here, is called the TNB frame. T for the unit tangent, N for the normal, B for the binormal, right? So let's just look at another curve here with this. Curve number 2. Okay, here's a Wilder curve. So we have a sine cosine, we have a t times the cosine, we have a cosine plus t times the sine. So you know these space curves can get crazy. So here we are right here. The purple is our unit tangent vector, and we start moving this along. And so that purple vector follows the curve, and so now notice they're kind of upside down here, and now here they're just going to all flip around as it goes through that loop. At all times, they stay perpendicular to each other. One thing I want to point out here with these, as I'm moving these around, the orange unit normal vector is always going to point on the inside of the curve. Notice right now the orange vector is pointing this way. Now, as I keep moving this, see if it will let me move this here, move. Oh, no, here, let's go back. Let's go back. And now here, let's see. Let me go all the way back. I wonder if this is a good one or not. Okay. Okay, it's pointing on the inside because that's the inside of the curve. Again, it's pointing on the inside of the curve, inside. Now the curve is flipping around, so that orange vector is now pointing on the inside of that loop up there, and then it flips around, and now it's pointing to the inside of that bigger loop. Okay. Wonder if another curve what that'll show. Here's another space curve. Let's see what these kind of look like here as we move these along. Now, this is kind of a good one. Notice here the curve is kind of curving down here. Our orange normal vector is pointing down. But when we keep moving this thing, our curve now is going to start curving upward. And notice that that orange normal vector now starts pointing upward. And we're going to go around. Now our curve is going to start going downward, and notice that unit normal vector went downward. Now it's still downward. Let's, go around. It just went upward. Okay, here it's down, but right around here, my curve is starting to go upward again, and that normal orange vector started to point upward again. So that unit normal vector always points in the direction that the curve is curving. All right. All right, let's see here. So let me take this down here and go back to this. All right. Now, let's look at the definitions of these things. The unit normal vector which is capital N of t, it's defined this way. It is the derivative of our unit tangent vector divided by the magnitude of that derivative of the unit tangent vector. So this is basically has length 1 because it's divided by its own magnitude, and it is the derivative of the unit tangent vector. Remember that thing I think it was right at the end of class last time that I said that if a vector has a constant length, that its derivative is going to be perpendicular to it. So notice t of t always has length 1 because it's a unit vector. This is the unit tangent vector. Thus, t prime of t, its derivative, is going to be perpendicular to it. And that's why, this is why the capital N vector is perpendicular to the unit tangent vector. Okay, that's the reason why that unit normal vector is perpendicular. It's because of, for that theorem that we talked about. All right. Now, let me put asterisk here that we want to remember is this, that n of t, the unit normal, oh, I'm sorry, you know what, while we're talking about asterisks here, the definition of the unit normal is something you need to at least passively be able to recognize, all right? The unit normal vector points into the curve also, or it points in the direction the curve is turning. In the direction the curve is turning. So that little fact, well, we need to just remember. Okay. Now let's then talk about the last of the three vectors. That's the binormal vector. That's our capital B vector, the binormal. And that's defined as the cross product of the t cross the n. Again, asterisk here, remember this definition. So this, of course, because it's a cross product, it's obviously going to be perpendicular to both of those vectors, right? Because cross product is perpendicular. So this means that B of t is going to be perpendicular to t, and B of t is going to be perpendicular to the normal vector. All right. And it's also going to have this. You can check this out for yourself. This has length 1. Okay. All right. Well, maybe I should mention, maybe this would be a good thing just to go over why this has length 1. Let's recall, what is the magnitude of two cross products equal to? So we do a cross product that gives us another vector that's perpendicular. There's a formula for what this magnitude is equal to. Does anybody remember? It's going to be the magnitude of the first vector. Yeah, times the sign. Magnitude of the first times the magnitude of the second. And actually, let's see. No, it doesn't even have to be an absolute value there. Times the sine of the angle between the two vectors. Okay. Now, in this case, our t, this is a unit vector. It has length 1. And our n, our normal vector, also has length 1. What's the angle between our t and our n vector? 90 degrees, or pi over 2. So this angle is pi over 2. The sine of pi over 2 is 1. So therefore, the magnitude of this b vector is also going to be 1, just like the other two. Okay. And it points in the direction using the right-hand rule. So that's another thing. The b direction points in the direction using the right-hand rule. All right. Okay. I think maybe we'll show that to just how that points like that. Where are we here? Oh, that's the wrong one. Okay. Ooh, no, no. And that's not it either. Let's do this. Mm-hmm. Okay, we can just use this one here. Now, the binormal vector is the blue vector here, all right? And so if you can see here, if we move this along, let's try, I guess here's a good place to see it. With the right-hand rule, we start with the purple vector, which is the t vector. We go around to the orange vector, the unit normal, and we see that it's pointed upward using the right-hand rule. Okay, I just want to illustrate that. Right. All right. As the last thing I want to do then in this section is basically, given a curve, I want us to find the normal vector and the binormal vector. Okay. So example. Let's say we're given our vector function is equal to the x component, the cosine of t. Oh, folks, I got to get that for you. Sorry. Okay. Cosine of t. The y component is the, no, I'm sorry. The y component is sine of t. And the z component is 1. No, it's t, sorry, t. So this is a helix. This thing is going, if we graph it, it's going to go up like this as a helix. All right. All right, so and we're going to want to find the unit normal vector and the binormal vector. Okay. So let's see. Let's just write down these formulas here. The normal vector is going to be basically t prime of t divided by the magnitude of t prime. Okay. So let's see what we get here. Well, to find t, we need to find, first of all, let's find r prime of t. Because remember, t, the unit vector, is r prime of t divided by the magnitude of r prime of t. So we need to get this first of all. Okay, what's our r prime? It's going to be derivative of the cosine is the negative sine. Derivative of the sine is the cosine. Derivative of t is just a 1. So therefore, its magnitude is going to be equal to the square root of the sum of the squares. That's going to be minus sine squared plus cosine squared plus 1 squared. That's all going to come out to be the square root of 2. All right? So therefore, our t, our unit normal vector, is going to be, it's r prime divided by the magnitude, so it's going to be 1 over the square root of 2 times r prime, which is minus sine t, cosine t, and 1. All right. Now, once we've got t, we can then, to get our normal vector, we have to get t prime. So we first had to get t, the unit, I'm sorry, this is the unit tangent, not the unit normal, unit tangent. So let's find t prime. Okay, it's still going to be 1 over the square root of 2. Okay, do the derivative again. Derivative minus sine is the minus cosine. Derivative of the cosine is the minus sine. Derivative of 1 is 0. And we are also then going to need to get its magnitude. So the magnitude of t prime is going to be 1 over the square root of 2. We're going to keep that times the square root of the square of the components. So minus cosine t squared plus minus sine t squared plus 0 squared. Okay, well, what are we going to get there then? Under the radical. We're just going to get 1. Cosine squared plus sine squared, we have 1. So it's basically, this is the magnitude of capital T prime is 1 over the square root of 2. All right, so we're ready to get the first answer here. So our unit normal vector then is equal to t prime divided by the magnitude of t prime. So t prime is 1 over the square root of 2 times, and the vector is minus cosine of t minus sine of t and 0 all over the magnitude of t prime, which is 1 over the square root of 2. So those two numbers, 1 over square root of 2, cancel each other out, and I'm left with my normal vector then is minus cosine of t minus sine of t. Actually, this thing, remember we told that this thing points to the inside of the curve, right? Oh, I'm sorry, I need a 0 here. Excuse me. I need a 0 for the last component. Where does this, let's see, if we're looking here just at the XY plane here, and so cosine and sine, that's going to just give us this circle that goes around, right? As we progress, we just go around the circle, the unit circle. And actually, this is going to be pointing, since we have negative numbers here in front of this, this is actually going to be pointing in this way with the negative numbers. So this really gives us something that's pointing on the inside of the curve. I think, yeah, that's going to be right. Just as an FYI, just showing that this normal vector points to the inside. Anyway, we've got our answer. That's our normal vector. So all we now have to do is get the binormal vector, and that is the cross of t cross the normal vector. All right. So the hard work's been done here already. So we get the cross product. Okay, what's our t vector that we got? The t vector is 1 over the square root of 2 minus times the sine of t, 1 over the square root of 2 times the cosine of t 1 over the square root of 2 times 1. Now, I could have just put that 1 over the square root of 2 out at the outside here. But I thought, okay, I'll just leave it in like that. So that's our t vector. And then where was our n vector? Oh, here it is, right here. Our n vector is minus cosine of t minus sine of t and 0. All right. So we get the cross product here. So for the I, when we cross out the first row and the first column, oh, let's go up further. When we cross out the first row and the first column, we're going to get 0, and we're going to just get a double minus, minus, so we're going to get 1 over the square root of 2 times the sine of t. 1 over the square root of 2 times the sine of t, that's going to be our I component. Now let's get the j component. We have to start out with a minus here. And we cross out our first row and middle column. Now we're going to get a 0 with the down diagonal. And then we have another double minus here with the up diagonal. So that's going to be 1 over square root of 2 times the cosine. All right. But remember, we got, let's just make sure we're clear on this. We got the double minus when we subtracted, but remember, we have to have a minus in front of it in the first place. So that still gives us a minus 1 over square root of 2 times cosine. And that's our j component. And then our k component, we then cross these out, and what do we have? Oh, we've got a lot of negatives here. Minus, minus, so that's 1 over square root of 2 times sine squared. And then we're going to have a double minus when we do the up, so that's going to be plus 1 over the square root of 2 times the cosine squared. And that's going to be our k component. All right, so that last component there, that just becomes 1 over the square root of 2 because we have sine squared and cosine squared. So our binormal then, if we write it with angle brackets, I can do it this way. Let me just bring out in front 1 over the square root of 2. That's going to be common to all of the components. And that's going to have sine t for the first, comma, minus cosine of t for the second. And the third one is going to be, the third one is just going to be a 1. Okay. Okay, so I think, yep. Now, I just want to point this out here. I could have made life a lot easier for myself kind of when I was finding this determinant. All of these items here in this row have 1 over the square root of 2. I could very easily have just carried that out here to the front of my determinant as 1 over the square root of 2, and then not had to deal with those here, but I would have had to then carry that over here for each individual item. Okay. So you've got this in the homework of computing this normal and the binormal vectors. Is there any question on this process? It can be maybe a little tedious, but you have formulas for these, and it's basically just following the formulas, is what I can tell you here. All right. Oh. Yeah, I do need to. Okay. So this is the end of 13.3. So 3 things that we talked about then. Let me just recap. We talked about how to find the 13.3 is the arc length. We have a formula for that. Curvature, we actually have two formulas for the curvature. And the third thing is finding T and B. And again, we have formulas for finding them. I mean, that's really 13.3 in a nutshell. I do need to get started, though, on 13.4 here so that we can make sure we get finished with that on Monday, because I'd like to spend Wednesday, which is a 2-hour period of time, I'd like to spend Wednesday doing problems, okay, and answering questions and having maybe you guys do some problems on Wednesday. All right, so 13.4, it's actually kind of about applications. It's about motion in space. And what we're talking about here is velocity and acceleration. All right. Now, what we're given here with all of these is we're given this as a position of the object. This r of t, this is our vector function. This is the position of the object in space, in 3 dimensions. All right. Now, we all know that velocity is change of position over change in time. So the velocity vector is equal to the derivative of the position vector. Okay, so this is the velocity vector, and it's the derivative of that, because we're talking about change of position over change of time. All right. Now, velocity, it has magnitude, just like it's a vector, it has magnitude and it has direction. It's a vector. But there's a part of velocity that we commonly talk about. We talk about how fast you're going, your speed. All right? Speed is a number, it's a scalar. So speed is the magnitude of the velocity vector. Equals the magnitude of the velocity vector. All right. In other words, it's equal to the absolute value of the velocity vector. And of course, this is equal to the absolute value of the derivative of the position vector. All right. Now, carry that to the next thing, acceleration. That's the change in the velocity over change in time. Change in velocity over change in time. So the acceleration is the derivative of the velocity. So a of t, a for acceleration, it's a vector also, it's the derivative of the velocity vector. Derivative of velocity vector. And this, in turn, is the second derivative, then, of our position vector. Second derivative, because the velocity is the derivative of the position, so the derivative of the derivative is the second derivative. The second derivative of r of t, the position vector. So I just want to look at one kind of problem here, just talking about these basic definitions. And so here's an example. I think it's very straightforward. Example, what we're given is the position vector. So we're given that r of t is equal to the following, t cubed times I plus t squared times j. All right. Notice this thing, this vector has no k component. So this is only on the xy plane. I could also write it using the angle brackets as t cubed, comma, t squared. I think we're just going to leave it like this. It doesn't matter. I'm just going to leave it as two-dimensional. No, let's not. Let's go on and just do it. T cubed, t squared, and let's go on and put the 0 there for the z component. Sorry about that. Okay. So the velocity then is the derivative of the position vector. So to find the velocity, we just do the derivative. So the velocity is 3t squared, 2t, and we're going to have 0 there for the third component. So this is the velocity vector. And then let's find what's the speed. The speed is the magnitude of the velocity vector. So that's going to be the square root of the square of the components. That's going to be 9 t to the 4th, squaring t squared, plus 2 2s are 4, t squared. The 0 just is 0. So this is our speed. And then finally, the acceleration vector, that's going to be the derivative of the velocity vector. So we just do the derivative again of what we had gotten. So here's our velocity vector. All I do is take the derivative again. So 2 times 3 is 6t. Derivative of 2t is 2. The derivative of 0 is 0. And that's our velocity vector. Okay. Notice, let's say at t is equal to 1, then our velocity is, let's see, our velocity at 1 is, let's plug this in here, 3, 2, and 0. Our speed is the magnitude of that. So that's going to be what? The square root of 3 squared, 9, plus 2 squared, 4, plus 0. So our speed, whatever dimensions we're talking about, is the square root of 13. And then finally, our acceleration at t equals 1. Where is that? Here it is, acceleration, 6t, that'll be 6, 2, and 0 for our acceleration. All right. Okay. So that's just one kind of problem. What we'll do next time then, there's only a little bit more with this section. I'm going to do a kind of problem that you are going to be seeing next week at some point. And then another type of thing that you're going to see in your homework and quiz, all right? So I think we should be able to get those in on Monday for the 50 minutes, and so we can have these sections finished up. So that's it. Have a good weekend, and I guess don't party too much on Sunday evening with the Super Bowl. We want everybody to be clear-eyed when they come in on Monday.